Now let's focus on the hardware implementing cache coherence entirely, in addition to giving the shared address space. And there are two possibilities if the hardware is going to maintain the cache coherence. One possibility is what is called a write invalidate scheme. And here the idea is, if a particular memory location is contained in all the caches, all these processes have fetched this particular memory location Y, and it's sitting in the private caches of all these processes. And if now processor P1 decides to write to this particular memory location, it changes to from Y to Y prime. When that happens, what we're going to do is the hardware is going to ensure that all of these caches are invalidated. So the way it is done is that the hardware, as soon as this change happens, it's going to broadcast a signal on the bus called invalidate memory location Y. So that's something that propagates on the system bus. And all these processor caches are observing the caches. And this is sometimes referred to as Snoopy caches. In a lighter vein, these caches are snooping on the bus to see if there is any change to memory locations that are cached locally. And in this case, if an invalidation signal goes out for a particular memory location Y, then each of these caches is going to say, do I have that particular memory location? If I do, let me invalidate it. So that particular memory location gets invalidated. So the idea is, if you have that particular memory location, invalidate it. If you don't have that memory location, ignore it, right? So if you don't have it, you don't have to bother. But if you particularly happen to have this memory location cached in your private cache, and if you observe an invalidation for that particular memory location, you go ahead and invalidate it. That's what is called the write invalidate cache coherence scheme. You may already be one step ahead of me, and you may be thinking what may be an alternative to doing this invalidation, and you may be right. You've thought of perhaps updating the caches. That's what is called the write update scheme. The idea here is, if this guy is going to write to this particular memory location, modify it to Y prime, what we do is, instead of invalidating it on the bus, if there is a capability in hardware to send an update for this particular memory location on the bus, you send it out saying that I modified this particular memory location, this is a new value. And if these caches happen to have the same memory location, they all modify it from Y to Y prime. And now all of these caches have the new value of Y, and the old value has disappeared from the system. So in this case, what we're doing is, if you have it, update it. Once again, you're snooping on the bus. Each of these processor caches is snooping on the bus. And if they see an update for a particular memory location, they're saying, well, let me modify it so that future accesses by my CPU will get the most recent value that has been written into this particular cache line. That's the idea behind write update scheme. Now, whether we are talking about the write update scheme or the earlier write invalidate scheme, one thing should become very clear in your mind, and that is, there is work to be done whenever you change some memory location that could conceivably be cached in the other private caches of the CPUs. In the invalidate scheme, you send out an invalidate message. If it's an update scheme, you send out an update message. And that kind of transaction that's going on is an overhead. And as a system designer, one of the things that we've been emphasizing all along is that we want to keep the overhead to a minimum. But you can also see immediately that the overhead is going to be something that grows as you increase the number of processors, as you change this interconnection network from a simple bus to a more exotic network, and also depending on the amount of sharing that is happening for a particular shared memory location.